guys, welcome back. Today we're going to be talking about polar covalent. So one of the things that you see here is I got a battery here, and we got a positive pole and a negative pole. And polar covalent is going to be creating these poles, just like you see on the battery. You're going to get a positive pole and a negative pole. Well, why isn't it ionic? Well, what happens in covalent bonding, you're sharing. In ionic bonding, you're stealing them, you're ripping them off. Well, polar covalent is kind of stuck between these two. I'm not quite ripping off the electrons, but I'm not totally sharing equally either. So let's just pretend, for the sake of argument, we're just going to ignore this word polar and just focus on the word covalent. We look at the periodic table of elements and we see hydrogen has a proton number or atomic number of 1. That means it has 1 proton, and unless otherwise stated, we're going to have 1 electron. Oxygen is going to have an atomic number of 8. That's going to mean it's going to have 8 protons, and unless otherwise stated, it's going to have 8 electrons. Same thing for this hydrogen down here. So let's just fill this in, and if you need more help on this, look at my other video on non-polar covalent bonding. So I got this first shell. I'm going to put 2 electrons in it. So this innermost shell is totally full. This next shell can hold a total of 8 electrons, but I only got 6 electrons to put in there. So I'm going to put in my 6 electrons. All right, 1, 2, 3, 4, 5, 6 electrons. This oxygen atom is not happy. So in order to become happy, it's going to have to do the evil S word, right? What we're going to do is we're going to share our electron with this hydrogen. This hydrogen is 1 electron, and it's not happy. Why? Because this shell right here can hold a total of 2 electrons. I only got 1 to put in it. Well, if it wants to be happy, it has to do the evil S word. It has to share. So I'm going to share my 1 electron with oxygen over here. And so because they're sharing their electrons, what happens is this is a single bond, right? Just like we did with regular non-polar covalent bonding. So this is a single bond. And so this hydrogen says, you know what? It's cool. It's just like I have 2 electrons in my outer shell. Oxygen's like, hey, look, this is kind of cool. Things are getting better. It's like I have 7 electrons in my outermost shell. 1, 2, 3, 4, 5, 6, 7. But it's not quite there to 8. We're going to share an electron. We're going to share an electron with this hydrogen. This hydrogen is going to share an electron with this oxygen right here. And so now, here's another bond. Look at this, right? Oxygen has 2 bonds. It has a bond with that hydrogen, and it has a bond with this hydrogen over here. And so this hydrogen is going to look at the world and says, hey, look, it's like I have 2 electrons in my outermost shell. Hey, it's like I have 2 electrons in my outermost shell. This oxygen over here is going to look at things, and it's going to say, look, it's like I have 8 electrons in my outermost shell. So far, you see nothing different than a regular non-polar covalent bond. A non-polar covalent is, alright, we're going to spend time over here with the oxygen, and then we're going to spend time over here with the hydrogen. We're spending just as much time with the hydrogen as we would with the oxygen. That's what would happen in a non-polar covalent bond. What's happening in a polar covalent bond? Well, what happens to a polar covalent bond, you're supposed to share your electrons pretty equally. Well, oxygen says, my share. I ain't sharing no electrons with the stinking hydrogen, right? That oxygen is just going to hog those electrons. They're not going to let them share with the hydrogen, right? Now, it doesn't completely rip it off, but it sure does try. The electron is going to spend most of its time around this oxygen. It's going to spend some time around the hydrogen. And so that's why it's not covalent, right? If I rip these electrons off and hydrogen never ever got to see its electrons again, that would be ionic. But because the hydrogen does get to see its electrons sometime, that is polar covalent. What's going to happen, if I completely ripped off the electrons here, this hydrogen would have a +1 charge. If I completely ripped off the electrons over here, this hydrogen would have a +1 charge. Because I have 2 extra electrons, each of these have a -1 charge, and I ripped them both off, I would have had a -2 charge. But that's not exactly what happened. I wasn't able to completely rip off the electrons. And so my charge is somewhere between 0 to +1. I'm somewhere between those for my hydrogen. I'm somewhere between 0 to +1. Why? Because I didn't quite rip the electron fully off, but I'm not completely sharing either, right? I'm not being totally equal, totally fair with sharing. This oxygen is going to have a charge somewhere between 0 to -2. Why? Because I'm not completely sharing electrons. I'm not going to be totally fair. You can hold my electron just as often as hold yours. Nope, it's hogging the electron. I'm making up numbers here for the sake of argument. Let's say I hog the electron 80% of the time, right? Well, I'm going to be that -2 a lot more often than I'm going to be otherwise. Why? Because I'm not totally equally sharing my electrons, because I'm being an electron hog. That's why this oxygen is going to be partially negative. Okay, so why do we care about this polar covalent bonding? Well, what this does is it sets us up for something else. This polar covalent bonding explains why water will dissolve table salt. If you put table salt in oil, it's not going to dissolve. Here's why. The chlorine in our table salt is negative. The hydrogen in our water is positive. It's not completely positive, but it's partially positive. This is going to hang out around that negatively charged chlorine atom. Everybody's happy. The chlorine is happy because it's being exposed to a partial positive. Hey, we're opposites. Opposites attract, right? That's one of the reasons why it's important, right? Same idea for the sodium. That's the Na in your table salt. It's going to want to hang around the oxygen. Why? The sodium is positive. The oxygen's kind of act like it's negative. Once again, opposites attract. Once again, the oxygen's not a full negative because I'm not able to fully rip off those electrons from the hydrogen, but I sure do try. That's why your table salt would dissolve in water. Why? Because water is polar, because it's not equally sharing its electrons. See, look, we got a positive pole over here, somewhere between 0 and +1, and we got a negative pole over here, somewhere between 0 and -2. Another reason why we care about this polar covalent is this creates something called hydrogen bonds. What happens is we got our water molecule over here, right here. These are our this is our polar covalent bond. But remember how this hydrogen is partially positive and this oxygen is slightly negative. Well, if I have another oxygen atom over here, what's going to happen is we're going to kind of get a bond between this hydrogen and this oxygen over here. So the hydrogen 1 atom is going to be a molecule is going to be partially bonded to the oxygen of a different molecule. This is going to explain several of the weird things that water does. And so this is just going to continue to happen over and over again, where we make a bond from the hydrogen of one molecule to the oxygen of a different. This explains why it likes to dissolve. For example, if you have oil, right, you put a gloop of oil in here, what's going to happen? You're going to be breaking up all these hydrogen bonds. And so the water's going to say, get out of the way, get out of the way. So we want that oil to break as little of these hydrogen bonds as possible. When you put your oil in a pan, right, it all forms these grease bubbles. These grease bubbles will fuse to produce a larger grease bubble, right? You go from a bunch of small grease bubbles to one big grease bubble. Why? Because we don't want to break up all these hydrogen bonds. Another thing that the hydrogen bonds do is it explains why it takes so much heat for water to boil. In order for this water molecule to go into outer space or, evaporate from the surface of your skin, what's going to happen is we're going to break this hydrogen bond here. We're going to break this hydrogen bond here. We've got to break this hydrogen bond here. And that takes a lot of energy. These hydrogen bonds, these are the weakest of all bonds, but they're about 1/10 as strong as a regular covalent bond right there. So in order for that water molecule to break and go and evaporate from the surface of your skin, you're having to break about 3 to 4 hydrogen bonds. You're having to use 30 to 40% of the energy in this bond right here. So that's a lot of energy right there. And so very, very powerful property there. Hydrogen bonds also explain why, for example, water bug can actually stand on the surface of the water even though it is heavier per ounce of space than water is itself. Why? So what's happening is when this bug is standing on it, this water molecule is it doesn't want to lose its buddy, it doesn't want to lose its friend over here. And so, look, it's easier to hold the bug than break this bond. It's also why you may have a cup of water that's full to overflowing, and the water doesn't fully run down the edge of the glass. I'd rather keep these bonds and then lose these bonds and run down the edge of my glass. These hydrogen bonds are very, very important in determining a lot of shapes in our body. We have proteins, and so we'll have a protein that's in this weirdo shape right here. And in order for it to work, it has to keep that shape exactly. Well, how is it keeping its shape? It has all these little hydrogen bonds, which are helping it stay in that exact shape. Our DNA, what's holding our DNA together? Hydrogen bonds. We might have a chromosome that's 1 billion base pairs long. Well, each base pair is being held together by 2 to 3 hydrogen bonds. So that's going to be 2.5 billion hydrogen bonds holding our DNA together. This hydrogen bonding is all coming about because oxygen's being an electron hog. It says, my share. It's not sharing its electron equally with the hydrogen. And so what's happening is you're getting a partial positive, right? I didn't fully rip off that electron, and I'm creating a partial negative. Why? Because I didn't fully steal the electrons from the hydrogen. That's why we got these charges, because electrons are not spending equal time with the hydrogen and the oxygen.
All right, that concludes today's episode. If you liked what you heard, be sure to click the subscribe and like button down below. And as always, if you have any questions, comments, concerns, or if there's any particular topic you'd like me to create a video on, let me know in the comments down below. All right, well, I look forward to seeing you on my next podcast.